Hi everyone. In this lesson we're going to look at the formal statement of Taylor's theorem and work through a few examples. So here is the statement of Taylor's theorem. Let's read through this carefully and understand what it says. So we start out with n representing some integer. We're given a function f of x, and we assume that the n plus first derivative of your function exists for all x in some given interval. So this alpha to beta, that just represents some interval in the real number line. We also pick a fixed point a that's in this interval. So a is just some fixed value that you are given within this interval. Then we have this statement. For every x in the interval, there will exist a number z that is between x and a. Then we have this equation right here which holds. So this equation states that f of x is equal to, and you will recognize this as being your nth degree Taylor polynomial for the function f of x expanded about the point a, plus, and this right here we call our remainder term. Now notice how this is written. It's the n plus first derivative of f evaluated at some point z, and that z is going to be somewhere between x and a. We just don't know exactly where it is, but we do know it exists. Divided by n plus 1 factorial times x minus a to the n plus first power. So the way you should understand this is you should realize that this term right here, which we denote as r sub n of x, that represents the difference between f of x and your nth degree Taylor polynomial. So you can think of it as an error term. For example, if we take this term over to the left, what we would get is f of x minus the nth degree Taylor polynomial equals Rn of x, which is this quantity right here. So this represents the difference between f and the Taylor polynomial. So we can think of this as being like an error term between f of x and your nth degree Taylor polynomial. Okay, so that is the formal statement of Taylor's theorem. And also just make sure you understand that if you're given the point a, now a lies in some interval alpha to beta, so say, your interval alpha to beta is like this. Okay, so there's your interval alpha to beta, and you pick an x somewhere in this interval, say right here, then make sure you understand that the z is going to be between the x and the a. So it's somewhere in between those two numbers, we just don't know where. So this is your point about which you expand your Taylor polynomial. Then x is just supposed to lie anywhere in this interval. And the z is always going to be between x and a. So if x is over here, then the z would be in here somewhere. Okay, so that's graphically how you should visualize the relationship between the x, the a, and the z. Z is always going to lie between x and a, and you should think of a as being a fixed value about which you're finding your Taylor series expansion. Okay, so that is the formal statement of Taylor's theorem, and it is very important to remember that this is what we call our remainder term. Now from the Taylor's theorem, we have this following corollary, and it simply makes this statement. If the remainder term, Rn, if that converges to 0 as n goes to infinity, so if this goes to 0 for all x in your interval alpha to beta, so if that goes to 0 for all x in the interval alpha to beta as n goes to infinity. Then basically this term is going to be going to 0, and you can replace this n up here, right here, with an infinity, and you can make the statement that f of x is actually equal to the summation from 0 to infinity of these terms right here. And that's what our next corollary states. So let's take a quick look at it, and then we'll look at some examples. So here's our corollary that comes from Taylor's theorem, and it simply states that if you consider the remainder term from Taylor's theorem, and you look at the limit as n goes to infinity, if this is equal to 0 for all z and x in your interval alpha to beta. Now remember, the z is always between x and a. All right, so as long as this goes to 0 for all x and z in your interval, then this quantity right here, notice we go from 0 to infinity, will exist. So this summation converges. It actually converges absolutely. And you can actually write that f of x is exactly equal to this infinite series. So notice we have an infinity up here now. So this series will converge for all x in your interval alpha to beta, and it will converge to f of x. Okay, so that's the statement of this corollary. Now let's take a look at a few examples. Now in our first example here, we want to find the Taylor series expansion for the function e to the x power, our friendly exponential function, expanded about a equaling 0, and we want to prove that that remainder term in the limit as n goes to infinity, it approaches 0 for all real numbers x. And then that will justify the fact that we can write e to the x as an infinite Taylor series expansion. All right, so to find the Taylor series expansion for e to the x about a equaling 0, remember we create this table down here. So here we have our n column. Here we have the nth derivative of our exponential function. Notice it's just e to the x is going all the way down. That's because the derivative of e to the x is e to the x. So as we take derivatives of this, we just get back e to the x. So notice we have e to the x going all the way down here. And then over here we have the coefficients that go along with our Taylor series expansion. Now in this case, the a right here, that a is going to be 0 for this particular example. So notice that when we put 0 in for this x, we get 1. When we put 0 in for the x here, we get 1 divided by 1 factorial. Well, that's just going to be 1 again. Then we put 0 in for this x, and we get back 1. And since we're dividing these by n factorial, we get 1 over 2 factorial, because the n is 2. Put 0 in here, we get 1 divided by 3 factorial. Once again, that 3 factorial is the n factorial that we're referring to right here. And now you can see a pattern. So it's going to go 1 over 2 factorial, 1 over 3 factorial, 1 over 4 factorial, 1 over 5 factorial, and so on. And so right here is our nth degree Taylor polynomial for the exponential function e to the x. Notice we have 1, that's this one right here, plus, and then we have a 1 times x minus 0 to the first power. Remember, a is 0. Okay. And then we have plus 1 over 2 factorial times x minus 0 squared, plus 1 over 3 factorial times x minus 0 cubed, and so on. So, and we keep going to x to the n over n factorial. This is our nth degree Taylor polynomial for the function e to the x, and notice that we can write it like this. Oh, and keep in mind here, these should be k's. So that is corrected in your notes. Those should be k's. Let's just check that out. Notice that if we put 0 in for this k and this k, we get x to the 0 over 0 factorial. That's going to be 1. If we put 1 in for this k, we get x over 1 factorial. So that's just this x. If we put 2 in for the k, we get x squared over 2 factorial. If we put 3 in for the k, we get x cubed over 3 factorial. And so on. Okay, so you see we are recovering this. So this is just summation notation for what we have written right here. Okay, now let's consider that remainder term. We still need to show that this holds. Okay, so you see, if we can show that this holds, then we are justified in writing that e to the x is actually the sum from 0 all the way to infinity of these terms down here. Okay, so if we can show that this holds, then this statement will have been justified. Okay, so let's take a look at that remainder term. Well, now let's just write out the statement of that remainder term. Remember from Taylor's theorem, okay, so remember that's our remainder term from Taylor's theorem. Now notice that the n plus first derivative of e to the x power is just e to the x. So this is just going to be e to the z. Notice we have a z there. Okay, and so, oh, and also notice that this a for our problem is going to be 0. And so we end up with this as our remainder term right here. So right there is our remainder term. E to the z divided by n plus 1 factorial times x to the n plus 1. And by Taylor's theorem, we can write e to the x as our nth degree Taylor polynomial plus the remainder term. And that's what we have right here. This is Pn, and this is Rn. Now we need to show that this approaches 0 as n goes to infinity. And then that will justify replacing this n right here with an infinity. Okay, well, if we consider that Rn now, let's notice this. So right here, we're considering the absolute value of our remainder term. So we just take the absolute value of it. Right here it is. Now notice that the z right here is supposed to be between 0 and x, because this is our a that we expanded our Taylor series about. So this is going to be less than or equal to, if we replace that z with the absolute value of x. Okay, once again here we have 0 here, x is here, z is supposed to be between 0 and x, so of course e to the z is going to be less than e to the absolute value of x. The reason we put the absolute value there is just in case x is a negative number. Then your z would be over here, but we would still have this holding. E to the absolute value of x would still be bigger than e to the z. Okay, so just keep that in mind. We have x to the n plus first power. That's coming from x minus a to the n plus 1. And so we have this inequality right here for the Rn terms. So we know that the Rn's, the remainder terms, are less than this quantity. Now we need to take the limit of this as n goes to infinity and verify that we get 0. Well, let's take the limit. So right here we have the limit of the quantity. Notice that this does not depend on n, so we can actually move it outside. So here it is moved out in front of the limit. And now we need to justify that the limit as n goes to infinity of x to the n plus first power divided by n plus 1 factorial is 0. Well, certainly that's going to be true. Now, think of the x as being fixed for the moment. What this is an exponential function, right? So think of the x as being like 3, for example. So, if we look at the limit as n approaches infinity, 3 to the n plus 1 over n plus 1 factorial. Just think of the x as being fixed, for example, the number 3. Now, if you think about this limit for a moment, you should be able to justify to yourself that this limit is going to be 0. Because, as we've said previously, factorials grow much, much faster. This goes to infinity at a much, much faster rate than this term goes to infinity. Now, infinity over infinity is not 0. What I'm just saying is that the denominator goes to infinity much, much faster than the numerator does. And to justify that, just let's write out what the numerator and denominator would look like for a particular value of n. So, for example, if n is 5 or 6, say, let's just write this out. Notice we'd have 3 times 3. Okay, so this would be when n is 5. 5 plus 1 is 6. Then in the denominator we would have, okay, now notice that these terms here, they're just like think of them as being a fixed constant. And then once n gets larger than 3, you see these numbers in the denominator keep growing. They keep getting larger and larger and larger. But these numbers up here in the numerator do not. They stay fixed at 3. So you see 3 over 4, that's going to be obviously 0.75, so that's less than 1. 3 over 5, that's even smaller. So 3 over 4 times 3 over 5, that's even smaller than 3 over 4, right? Then you're multiplying that by 3 over 6, which is 1/2, and that's going to make this quantity even smaller. And so you see you keep going like that. So taking this quantity here, which is already less than 1, and then multiplying it by another number that's less than 1 is going to make this even smaller. And it just keeps getting smaller and smaller as we multiply by more and more numbers that are less than 1. So you should see that this limit is equal to 0. Okay, so now we have justified that our remainder terms go to 0 as n goes to infinity for any x. It doesn't matter where x is in the real number line. And so we've just justified this statement. So therefore, we can actually write by the corollary that e to the x is equal to the summation from 0 to infinity of x to the k over k factorial. So we have just justified writing e to the x like this. So in other words, just writing out that summation, what that means is for every x, e to the x is actually 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4th over 4 factorial plus, and it just keeps going. If we go all the way to infinity, these numbers or this series will converge to the number e to the x power, whatever value you put in here for x. So we have just justified that because we justified that the remainder term in Taylor's theorem approaches 0 for every x. Let's take a look at another example. Now in this example, we want to find a Taylor series expansion for the cosine function expanded about 0, and we want to prove that the remainder term also goes to 0 for all x. So to construct the nth degree Taylor polynomial first, remember we create this table. Now in the second column here, notice that we have our nth derivative of the cosine function. So derivative of cosine is negative sine. Derivative of negative sine is negative cosine. Derivative of negative cosine is positive sine. Then it goes cosine, negative sine, negative cosine, and so on. Now we want to evaluate the coefficients of our Taylor series polynomial. Keep in mind that the a here is 0 for this particular example. So putting 0 in here for x, we get 1. The cosine of 0 is 1, remember. Putting 0 in here for x, the sine of 0 is 0. When n is 2, negative cosine of 0 is negative 1, and we divide by n factorial. So negative 1 over 2 factorial, that's our coefficient that goes with the x squared term. Okay, and then continuing in this manner, sine of 0 is 0. Cosine of 0 is 1, and then we divide by 4 factorial. Negative sine of 0 is 0, and negative cosine of 0 is negative 1, and we divide by 6 factorial. So now we see a pattern: 1, 0, negative 1 over 2 factorial, 0, 1 over 4 factorial, 0, negative 1 over 6 factorial. So we see that whenever n is odd, the coefficients are 0. So in other words, your Taylor series expansion for the cosine function will contain no odd powers of x. Okay, so then right down here we have our Taylor series expansion. So notice that we go 1 minus x squared over 2 factorial. 1 over 2 factorial is coming from right here, plus x to the 4th over 4 factorial. That's coming from right here. Notice that we didn't have any x cubed term or x term because they were 0. The coefficients that go along with those were 0. Minus x to the 6th over 6 factorial. That is coming right from here, and so on. And then we go all the way out to x raised to some even power. Notice how we wrote the even power as 2 times n. So we make sure that the exponent there is even. And we divide by 2n factorial. And then we have our remainder term r sub 2n. Now we want to show that this goes to 0 then. Okay, now notice that we can write this as follows. So this is your Taylor polynomial right here. It's actually of degree 2n. We put the 2n there just to make sure that we end with an even power of x. You don't have to do that, but that's what we've done here. Notice that we can write that like this. So we consider the summation from 0 to n, negative 1 to the k. That'll give us the plus, minus, x to the 2k. By having a 2k here, that will go in even powers. So when k is 0, we have x to the 0. When k is 1, we have x squared. When k is 2, we have x to the 4th. When k is 3, we have x to the 6th, and so on. And then we end with our remainder term right here. Now you notice that we have the sine function written right here. That's because the Rn right here, let's recall what the Rn was from Taylor's theorem. From Taylor's theorem, recall this. This is your remainder term. Okay, so that was your remainder term from Taylor's theorem. Now in this case, we're considering r sub 2n. So this is actually going to be a 2n in here, so let's just change those to a 2n. And then plus 1. Now it is a fact that the 2n plus first derivative of cosine is either going to be plus or minus sine. Notice this is an odd number. And if you look back at our table here, you see whenever we have an odd n, like 1, 3, 5, the derivative of cosine was negative sine or positive sine. You see that. So that's why we have that sign of z right there. And then we divide by 2n plus 1 factorial times x to the 2n plus 1. Now, we need to show that this approaches 0 as n goes to infinity. Okay, so that's going to be very similar to what we did before, noting that factorial functions grow much, much faster than exponential functions. So let's take a look at that. So right here is our remainder term once again. Now if we take the absolute value of it, we get this right here. Okay. Notice that the absolute value of this quantity is always less than or equal to 1, right? The sign never gets any bigger than 1. So we can basically just get rid of it, replace it with a 1, and we end up with this. So you notice we just replace this with the number 1, we end up with this. Now, the limit as n goes to infinity of x to the 2n plus 1 over 2n plus 1 factorial, that's going to be 0 by the same reasoning that we talked about previously. This is a factorial function. It goes to infinity much, much faster than the numerator, which is an exponential function. So once again, the reason this is 0 is because the limit as n goes to infinity of a to the n over n factorial is 0 for any base a, any fixed base a for this exponential function. And so that proves that this remainder term right here goes to 0 as n goes to infinity. And so we are justified in writing that the cosine function is actually the summation from 0 to infinity of these terms right here. And that's what we have right here. Okay, so we've justified that the cosine function can be written like this. Notice this is the sum from 0 to infinity. And notice that that is just 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial. The next term would then be plus x to the 8th over 8 factorial minus x to the 10th over 10 factorial, if you wanted to write out a few more terms, plus, and then it keeps going in even powers of x. Okay, and in a similar manner, you can do the same thing for the sine function, except the sine goes in odd powers of x. Notice down here, you could do the exact same thing up here with the sine function, and you see the sine is the sum from 0 to infinity. Notice we have x to the 2k plus 1 over 2k plus 1 factorial. This gives you odd powers of x. And the negative 1 to the k right here, that gives you the alternating sign pattern that is required. And it's also interesting to note that the reason you have even powers for the expansion of cosine is because it's an even function. If you think back to its graph, it is symmetric about the y-axis. And all of these functions, x squared, x to the 4th, x to the 6th, those are all symmetric about the y-axis. In other words, they are even functions as well. So it makes sense. Sine if you think back to what an odd function is, sine is an odd function. And all of these functions over here, x, x cubed, x to the fifth, x to the seventh, they're also odd functions. So it makes sense that this would be your expansion for sine. It only involves odd functions. And your expansion for cosine only involves even functions. So that makes sense. Let's take a look at another example. Now in this example, we would like to find the necessary degree of the Taylor polynomial expanded about a equaling 0, which will approximate the cosine function to within 10 to the negative third over the interval from negative 2 pi to 2 pi. Now recall from our previous examples, we have deduced that the cosine function can actually be written like this. So this is our infinite Taylor series expansion. We've determined that this does converge to the cosine function because the remainder term went to 0. Now what we want to do with this problem is we just want to approximate the cosine function to within 10 to the negative third for x being between negative 2 pi and 2 pi. So we want to determine how far out in this expansion do we need to go to get this degree of accuracy for x in this interval range. So perhaps we only need to go out to x to the fourth over 4 factorial. Maybe this polynomial will do. Or maybe we need to go a little further. Maybe we need to go out to x to the 8th over 8 factorial. So we want to determine how far out in the expansion do we need to go so that our Taylor polynomial will approximate the cosine function to within 10 to the negative third for all x in that interval. Okay, so what we do is we will analyze the remainder term that we have down here from Taylor's theorem. Now notice that for the cosine function, the n plus first derivative of cosine is either going to be plus or minus cosine or plus or minus sine. Okay, now it doesn't matter which one we end up with, cosine or sine. The fact is that both of these are bounded between negative 1 and 1. So if we consider the absolute value of our remainder term, so that's what we're doing right here, notice that we can write it like this. So here we just took the absolute value of it. Since this term in the numerator right here is always going to be less than or equal to 1 in absolute value, we can just replace this with a 1 and state that this quantity here is going to be less than or equal to 1 over n plus 1 factorial times 2 pi to the n plus 1 power. Now how did we get the 2 pi right here? Well, keep in mind for this problem the a is 0 and the x is always going to be less than or equal to 2 pi because it has to be in this interval. So the absolute value of x is always going to be less than or equal to 2 pi, right? So that's how we got that 2 pi right there. Okay, so what we're going to do now is we know now that the remainder term is less than this quantity. We will set this less than 10 to the negative third and solve this inequality for n. Well, we're not going to really solve it for n because we have a factorial down here. We can't really explicitly solve it for n, but we can plug numbers in for n until, and we can evaluate these on the calculator, we'll plug numbers in for n until this quantity is less than 0.001, and then that's how we'll determine what n is. Okay, so that's what we're doing down here. So right here is the inequality that we need to solve for n. Well, we can't explicitly solve this for n. So we can't isolate n on one side and put everything else on the other side because of the factorial here. So what we have to do is just plug numbers in for n until this becomes smaller than 0.001. Now you'll find that if you do that, n needs to be 21 or larger in order for this to be smaller than 0.001. So if you put 20 in for the n here, you'll find that this is a little bigger than 0.001. Then if you put 21 in here for n, you'll find that it's a little bit smaller than 0.001, and that will remain true as long as n is bigger than or equal to 21. So therefore, P21 will approximate the cosine function to within 0.001 for x between negative 2 pi and positive 2 pi. Now in this case, P21 for the cosine function is actually the same as P20. And that's because if you look at P20, that's the sum from k equaling 0 to 10 of this quantity right here. Notice if we put 10 in for the k right here, we get x to the 20 power divided by 20 factorial. Now the next term, x to the 21 power, that has a 0 coefficient, right? The cosine expansion has no odd powers of x that go with it. So because of that, P21 is actually the same as P20. Because once again, if we added in x21 here, the coefficient that goes with this is actually 0. Okay, so actually P21 and P20 are the same in this case. So this is the polynomial that we need right here. This is actually the same as P20. Or you could say that this is P21. They're the same thing. This will approximate the cosine function to within 10 to the negative third over this interval. And that's how we solve this problem. So once again, we had to analyze our remainder term. We found that it was less than or equal to this quantity. And then we set this less than the desired error. And then we determined what n had to be. Now in this example, we want to approximate the exponential function e to the x to within 0.001 again, that's 10 to the negative third, over the interval from negative 3 to 3 using a Taylor polynomial centered at 0. Let's find the necessary degree for that Taylor polynomial to accomplish this. So once again, we have to analyze that remainder term. Now let's recall that the exponential function e to the x can be written like this. So here's your Taylor polynomial plus your remainder term. Now the Taylor polynomial, remember, it looks like this. Now remember, that is okay, so that's your nth degree Taylor polynomial. And then this is your remainder term right here. Notice that we have an e to the z here. That's because the n plus first derivative of our function, which is e to the x in this case, is just e to the x, but we put a z in there, okay? So we have e to the z. That's why that e to the z is right there, because the n plus first derivative of e to the x is e to the x. This x right here, the a is 0 in this case again, so that's why we have x minus 0 to the n plus first power there. So now what we need to do is take this quantity and set it less than or equal to 10 to the negative third, and then find out how large n has to be. Now before we do that, we do need to find a bound for this e to the z. We don't want that there. Well, let's notice that the biggest that this can be, the biggest this term could ever be, is e to the third power. And that's because x is supposed to always be between -3 and 3, and z is going to be between x and 0, so z has to be in this range as well. Okay, so what we do now is we take the absolute value of our remainder term, right here it is. We know that it is less than or equal to e to the third power divided by n plus 1 factorial times 3 to the n plus 1. The reason we have this 3 here is because we know that the biggest x can be is 3. So this term right here will be less than or equal to 3 to the n plus 1. Okay, so that's how we get this inequality down here. And now all we need to do is set this less than 10 to the -3rd, or 0.001, and figure out how large n has to be so that this is satisfied. Now once again, you can't explicitly solve this for n because of the n plus 1 factorial, so we have to just plug numbers in for n until this is satisfied. Now if you do that, you'll find that n has to be bigger than or equal to 14. If you put 13 in here for n, you'll see that it's a little bit bigger than 10 to the -3rd. If you put 14 in for n, you'll find that it's a little bit less than 10 to the -3rd, and it will stay that way as long as n is bigger than or equal to 14. And so therefore, P14, which is just the summation this polynomial will approximate e to the x to within 0.001 as long as x is between -3 and 3. And that completes this example.